The somatosensory system and balance control. The somatosensory system consists of mechanoreceptors, their sensory innervations, and central pathways. Muscle spindles are mechanoreceptors that detect both the velocity and length of muscle stretch. Primary spindle endings, innervated by large group Ia afferent fibers, are sensitive to stretch velocity, whereas secondary endings, innervated by smaller group 2 fibers, along with Ia fibers, detect stretch length. These spindles contribute to kinesthesia, the perception of joint movement, as well as joint position sense. Golgi tendon organs, located at the muscle-tendon junction, transmit information about active muscle tension. Joint receptors, meanwhile, respond to mechanical deformation of the joint capsule and ligaments. Together, muscle spindles, Golgi tendon organs, and joint receptors provide proprioceptive sensation. During upright standing, movements between the feet and the base of support generate shear and vertical forces that activate cutaneous mechanoreceptors. Cutaneous input appears to detect low-frequency body sway, such as that occurring during quiet stance, and also provides information about body orientation relative to the ground. Studies involving foot-sole vibration and lateral platform translations have demonstrated that while vibration influences postural responses, cutaneous input itself plays a minimal role in triggering corrective reactions to balance perturbations. Additionally, the effects of foot-sole vibration are less pronounced during standing compared to sitting. Cooling the plantar surface has only a marginal impact on postural control, despite its anesthetic effects. Collectively, these findings suggest that foot-sole hypoesthesia caused by disease is unlikely to be a major contributor to postural instability in patients. Light fingertip contact with a stationary surface significantly reduces body sway during quiet stance and diminishes leg muscle responses to perturbations. Interestingly, this stabilizing effect occurs even before physical contact is made, indicating a close association between the intention to touch and the suppression of postural adjustments. It has been proposed that an external contact point serves as a reference for vertical orientation. Supporting this, light finger contact can counteract the disorienting effects of neck muscle vibration. Conversely, touching a moving surface increases postural sway, suggesting that individuals integrate cutaneous input from the fingers with arm proprioception to maintain balance. Proprioception provides information about both static and dynamic joint position and orientation, playing a key role in the perception of verticality. Input from the lower limbs and ankles is particularly critical for postural control. Proprioceptive signals, and thus body orientation, can be distorted by muscle vibration. For instance, vibrating the soleus muscle in standing individuals elicits action potentials in Ia afferent fibers, creating an illusory sense of triceps surae lengthening and inducing backward body sway. In contrast, vibrating the dorsal neck muscles produces forward sway. Proprioceptive input from leg muscles contributes to low-level ankle stiffness regulation, which helps counteract gravity during quiet stance. However, proprioception is not essential for maintaining balance in this context, as no direct relationship exists between triceps surae activity and lengthening caused by body sway. This implies that balance corrections do not rely solely on stretch reflexes triggered by ankle muscle elongation.